Hi, I'm Natasha Stark, an undergrad in the MIT BE department, and I'm going to share my design and model for determining parameters of a cancer sensing circuit.
Viruses can fight the deadliest cancers. We all know that cancer is bad. It takes the lives of hundreds of thousands of Americans every year, and millions more across the globe. Cancer is a leading cause of death, and many biologists have devoted years of study to defeating it. Pancreatic cancer is particularly bad because, upon diagnosis, it is usually very far advanced. Additionally, pancreatic cancer has some resistance inherent to the pancreas and is difficult to physically access due to being inside the abdomen and deep inside the abdomen cavity. Therefore, it needs a special type of treatment. Oncolytic viruses are viruses that target cancer cells specifically, either by specifically invading them through surface recognition or through conditional replication, based on the expression of different genes within the cell. Oncolytic viruses can be delivered systemically, treat metastases, and leave the healthy cells intact. And in fact, they often increase the immune response against a tumor, helping the body recognize what is unhealthy for it. So, how exactly would we target an oncolytic virus to a cancer? We can target a virus to a tumor by using the distinct expression of cancer cells. Certain genes are upregulated in cancers, and so their promoters are more active. One of those genes is telomerase, which is an enzyme that recreates the ends of DNA, thus protecting it from the damage of replication. It is known to be upregulated in 85% of cancers, although the exact method of its regulation is unknown. Cyclooxygenase 2 is another enzyme found only in highly proliferating cells, and cyclooxygenase 2, the second isoform, is almost exclusively found in tumor cells. Both of these proteins are fairly specific for cancer, and so their promoters are only active in cancer cells. So, we can use these two promoters to target cancer by incorporating them into the virus and making them necessary for the virus to express its own proteins, replicate, and lyse cells. So what exactly would that look like? Our desired behavior would be for the telomerase promoter and the cyclooxygenase promoter, when they are both active, to instigate the production of a virus protein, such as E1. But we want them both to be necessary and neither one to be sufficient. So this is like an AND gate in a logical circuit. Obviously, this is a very simple diagram. To make it into a real biological circuit, we need to add in some more elements. The exact biology would look like this. We have the cell's natural regulators controlling our two artificial constructs, and then that runs through a layer of mRNA and protein production to another set of constructs that represses our final viral production. There's a lot of pieces here. It's a lot to take in. So I've simplified the biology here. Let's start at the top. We have two artificial constructs with our two promoters of interest. They're controlling repressors, LAC-I and TET-R, which control two different constructs with the same protein produced from them. This is the essential part of the AND gate, the fact that you need both of them to totally shut down Ara-C production. Ara-C is what represses the production of E1, that viral protein that's going to cause danger to the cancer cells. Without both LAC-I and TET-R preventing any expression of Ara-C, E1 will not be expressed. In normal cells, that is the safety. So, if this were a logic gate, what would our inputs be and what would our output be? It's pretty straightforward. The expression of hTERT and COX-2 are the two inputs, and the output of our AND gate is E1, which will lead to viral production. Let's look at the model and break it down, shall we? We have a system of differential equations that describes different parts of the circuit. The first part is production of LAC-I from the hTERT promoter. And because I've simplified transcription and translation into one term, it's a very simple term. CP stands for copy number. The second part of this differential equation is the interaction between LAC-I and the construct it represses. So the DNA binding activity of LAC-I. That's represented by the K-on and K-off, and how it interacts with the concentration of that construct in the cell. The last term is just protein degradation. And that's our first equation. It's actually our second equation too, because the interaction between COX-2, TET-R, and the construct that it represses is effectively the same. The next equation we're going to look at is skipping ahead a couple steps in the model. It's the production of E1, and how that is regulated by its repressor, RSE. So the first term is a bit of a doozy. It's the natural production rate of the promoter multiplied by the concentration of the promoter multiplied by the Hill term for repression, which includes the repression constant and the concentration of the repressor protein. You'll also notice this additional term here that might not be familiar to you. Because the Hill equation is normally used to account for the overall concentration of the repressor, and my equations have separate terms for the overall free concentration of repressor and bound concentration of repressor, I've included the bound repressor in this term to make the model more accurate to what is actually occurring in the cell. The next term is just degradation. It's pretty simple. I've also included a basal expression term here, because we all know that cells tend to have leaky expression. The next term is the rate of change of RSE. It's got several pieces since it is produced on two different constructs, and it also includes that Hill equation for repression. The first term has the Hill equation for repression by TET-R and by LAC-I on the two different constructs. So you'll notice that each one is multiplied by the concentration of its own promoter, and that I've done the same inclusion of promoter complex in the concentration of the repressor. These two halves here are the same, and we multiply them both by the average production rate. The next term is how RSE interacts with the promoter it controls, the K-on and the K-off of binding and unbinding to the DNA. Then we have the degradation rate. Altogether, that's our circuit, the AND gate that can be described by these equations. So what do we learn by modeling this? One of the things we learn is that copy number of the circuit and steady state of the E1 protein it produces are proportional. This makes a lot of sense when you realize that copy numbers in the single digits are definitely your limiting factor. What is interesting to note is how linearly they increase, though. You'll see in the line I've drawn from copy numbers 1, 2, and 3. And then if we look at 10 and 100, the next two charts, they have the exact same shape, just a different order of magnitude on the scale. Something else that we learn is that very little HTERT and COX-2 activity is needed to trigger the circuit. You do still need both of them, but considering how low our copy number is, it isn't surprising that it doesn't take a lot of activity to saturate the circuit. So here I have three different charts with the activity of HTERT and COX-2 set to some very low percentage of the regular production rate and the activity rate of the RSE promoter that directly regulates E1. When LAC and TET-R are just 1,000th of the regular production rate of the cell, you still have E1 expression. We go down another order of magnitude, and you still have E1 expression, though you'll see there is that spike in the RSE that controls it. By the time you get down to the next order of magnitude, 10 to the negative 5, the spike of RSE is far too high, and the steady state can control the E1 production and prevent it. However, that is a small fraction, and that is very useful to know when determining your therapeutic margins. One last thing I would like to share about my analysis of my circuit is the minimal effect that increasing the Hill constant can have. I draw this back to the low copy number as well. Here on the left, you'll see three charts. Each of these is the circuit modeled with the Hill coefficient and as a different number. The copy number is 1. You'll see a very large difference in behavior between graphs 1 and 2, or Hill coefficient 3 in the middle, and no noticeable change when the Hill constant jumps from 3 to 5. I believe that's because it doesn't take very much era C to saturate the circuit and that construct when the copy number is 1. On the right, I have a graph where I increase the copy number to 100, and you'll see that that shape is a lot steeper and a lot different than the two previous. By increasing the copy number, you allow more nuance into the system, and there's more factors that come into play before you saturate. That is my circuit design and analysis. I hope that this video was informational and that you are convinced of the therapeutic potential of oncolytic viruses. Thank you.